Hello everyone, and welcome to our series on building an end-to-end big data pipeline. Today we are diving into the third installment where we'll focus on consuming data from Kafka and storing it in AWS S3, our data lake. If you're new here, don't worry, I'll quickly recap what we have achieved so far. In the previous videos, we set up a powerful data generator and populated our database with the generated data. Then we seamlessly streamed this data into Kafka topic. Now it's time to take the next crucial steps in our pipeline journey, focusing on consuming data from Kafka topic using industry standard code, which you can find on my GitHub repository. I've shared the link in the description. You can follow that. Today we'll containerize Kafka for easy deployment and host our Kafka cluster on Google virtual machines, leveraging the cloud's capabilities. Additionally, we'll containerize our Spark-Scala code, enabling us to process large datasets with ease. By the end of this video, you'll witness the seamless flow of data from Kafka to AWS S3. We'll leverage the benefits of containerization and cloud deployment, empowering us to handle big data challenges with confidence. So without further ado, let's jump right in. Before we begin, head over to my GitHub and grab the startup v2 repository. Inside, you will find the DataGenerator code and a Docker Compose file containing all the necessary infrastructure. Create a new folder called Data Populator and place the repository inside. We'll be using the Docker Compose cs3.yaml file, which is similar to the existing Docker Compose.yaml file but with minor port changes. So first things first, go to AWS IAM. Click on Users in the navigation pane. Provide any suitable name as the username. For instance, let's call it S3 Full Access. Click Next. Select Attach Policies directly. Then search for Amazon S3 Full Access policy and select it. Then click Create User. Please remember that in production, you should not give S3 full access. We'll address security concerns in upcoming videos. Now, click on the newly created S3 full access. Go to Security Credentials, then Access Keys, then click on Create Access Key. Select application running outside AWS. And provide a suitable description. Once created, make sure to download your access keys and save them securely. We'll use them in our code. Great. To continue building our data pipeline, we'll create another folder called Data Migration. Inside this folder, we'll clone the ecart-migration repository, which contains essential Scala code for consuming streaming data from our Kafka topic and efficiently populating it into AWS S3. Let's go ahead and clone this repo into our folder to kickstart. Let's start by looking at the project structure. Here we have a Scala project that contains various components for batch and streaming jobs. The components will explore our job trait, job enum, and job factory. Job trait serves as a blueprint for job implementations. It defines the common interface that all job classes should implement. Here we have a logger variable which is used for logging job related information. Next, we have the job enum object. This is an enumeration of different job types that our project can handle. In our case, we have defined ecart fact order as one job type. You can expand this list by uncommenting additional job types. And we have the job factory object. This is a factory that creates instances of the job trait based on their specified job enum. The create job method takes a Spark session and a job enum as input. It uses pattern matching to determine the job type and returns the corresponding job instance. Let's come to ecart fact order job. The ecart fact order job inherits the properties and behaviors defined in the job trait, including the logging capability for monitoring job progress. The job starts by setting up its configuration. It specifies the Kafka bootstrap servers, the topic to consume data from, the starting offset, and the checkpoint location. The job reads data from the Kafka topic, which is in JSON format. To extract relevant information from the JSON payload, we use the JSON tuple function provided by Spark-SQL. This allows us to create a data frame with columns for the operation, the data after the operation, the timestamp of the operation, and the log sequence number LSN from the source. After parsing the JSON data, the job writes the processed data to a Parquet file format. The output is appended to a specific path in our S3 bucket, which is dynamically created based on the current timestamp. Now come to controller. The base controller sets up the Spark session by specifying the master URL and application name. Additionally, it loads S3 credentials from the configuration file loaded in config folder. Just now we downloaded access credentials. Make sure you change these credentials with that. Stream Kafka consumer ecart fact order 1. This controller is responsible for invoking the ecart fact order job. It extends the base controller, inheriting its Spark session and S3 configurations. Let's continue by setting up our Kafka cluster using the provided Docker Compose file. As we covered this Docker Compose setup in a previous video, you might already be familiar with it. Navigate to the infra directory inside starter v2 and execute the command docker compose -f docker compose cs3.yaml up to start the Kafka cluster. It appears that the Kafka cluster is now up and running. To avoid seeing the logs in the terminal, let me stop it and rerun it in detached mode. Now our Kafka cluster is running smoothly in the background. Open Kafka UI on localhost port 3333 and check Kafka cluster. We can check the status of our Kafka cluster and the available topics. Everything appears to be up and running smoothly. Also, there is no Kafka connector now. We need to create one. So let's do that. Before we proceed, we need to ensure that our database is running in the background and can receive traffic from our localhost. To achieve this, we'll whitelist our public IP. It's the same process we covered in the last video, so let me quickly walk you through it. First, head over to Google Cloud, navigate to the database and check the connection settings. Whitelist your public IP so that your database can receive traffic from your localhost. Once done, you can verify the connection through pgadmin. If everything is set up correctly, you should see a successful connection. Now let's move on to the next step. We'll check the total record present in the fact order table in the database. Once we have this information, we'll create a Kafka connector to enable data flow between our database and Kafka topics. To create the Kafka connector, open Postman and adjust the host name and password as per your configuration. Provide a topic name. In my case, I'll use sixth topic as it is the 6th attempt I have made before recording this video. Copy the host name from the public IP of your Google Cloud PostgreSQL instance and paste it into Postman. Then hit the post request. Now, if we head over to the Kafka UI, we should see the connector listed along with the topic name. To verify the data is flowing correctly, let's go to the topic and see if records are coming. Now let's load data to our S3 bucket. Open your IntelliJ and navigate to the config section. Inside dev-s3.conf, ensure that you have entered the proper AWS access key and secret key which we downloaded earlier in the video. Next, head over to the ecart fact order class where we'll configure the connection to our Kafka cluster. Make sure that the Kafka bootstrap server are set to localhost 9092, 9093 and 9094. Choose the correct topic name to subscribe to and ensure that the destination bucket in AWS S3 is already created. In my case, I have named it eCart Sales Data Lake. Moving on, we need to set up the checkpoint local name as checkpoint test topic 12 to store essential metadata and offsets. Additionally, define the path where the actual data from the topic will be stored. Let's name it temp test 12. The output is dynamically appended to the temp test folder based on the current timestamp. Now it's time to execute the process. Head to the controller and run it to load the data into AWS S3. Let's go to the AWS S3 dashboard to validate if the folder is created and data is being successfully inserted. Yup, looks like folder is created. And now keep refreshing. And we'll see data also getting loaded. Yeah, we have successfully loaded data, but we want to ensure continuous streaming for real-time insights. To achieve this, we'll use the DataGenerator from my GitHub Startup v2 repository. Go to chapter 2. Copy the provided docker build command and run it in the terminal inside DataGenerator folder. If you encounter any issues or see no activity, just double check the hostname and password in the DataGenerator file. Also, ensure that the table is already created as we have covered in previous videos. Looks like my URL is itself wrong. So let me fix it. Let's copy the IP address. You can copy it either from Google Cloud Public IP or from pgadmin. Let me fix it and rebuild Docker image and rerun it. Once the data generator is running smoothly, verify that data is being populated inside PostgreSQL from pgadmin. Yup, looks like it is populating. Let us see the same in Kafka UI. Here also we can see messages are coming. Finally, let's head back to AWS S3. Upon refreshing the page, we'll witness multiple Parquet files coming in confirmation that our data is streaming seamlessly into AWS S3. So yeah, we have covered the major portion till now. Let's now shift our focus to running the script using a Spark Submit, as this replicates the production environment. To achieve this, we need to build an artifact. Go to File in IntelliJ, then select Project Structure, Artifacts, then jar. In the main class dropdown, select controller, whatever the main controller is. I'm having this one as the main, and click OK, followed by apply and OK to save the settings. Now go to build artifacts, select the jar and click build to generate the artifact. Please be patient as the build completes. Let's run Spark-Shell to ensure it is running fine locally. Yup, looks like it is. Now it's time to run a Spark Submit using the jar we just built. You can find the specific Spark Submit command in the video description. Let's head over to S3 and verify if the Parquet file is created. Yup, we can see a new timestamp folder is created in S3 and within it we can find the expected Parquet file. With successful testing completed, it is time to move forward with our big data pipeline. Let's first stop the containers, ensuring a clean state before proceeding to the next stage. Perfect. Now that our containers are stopped and our local environment is neat and tidy, it's time to take our Dockerized Kafka cluster to the cloud. Let's move on to setting up a VM instance on Google Cloud with an Ubuntu image. Since we'll be using Kafka Connect on this instance, we need to whitelist our public IP to interact with Kafka Connect and access to the Kafka UI. First, go to the VPC firewall rule and check the default allow HTTP section. Here I have already whitelisted the IP for the ports used by the Kafka cluster. However, my public IP might have changed, so let me fix that by updating the IP and remove any unrestricted access. This is my IP, let me whitelist it. Putting it in CIDR format and save it. Now we can conduct a connectivity test for my IP. Let's click create and provide a test name. In the destination IP address, put the VM's public IP and choose a port number that has been whitelisted. In the source, I'll put my public IP. This test will determine if the connection is reachable. Yup, it's reachable. Now let's proceed by directly doing SSH into the machine and let's install Docker there. Now it's time to run Docker Compose inside our VM. The only difference between the current Docker Compose and the one for the VM is the Kafka advertise listener parameter. We need to change it from localhost to the public IP of our VM. Let's copy the VM's public IP and paste it into the Docker Compose file at all these three places. After making this change, we can deploy it on the VM. Oh, we have encountered an error stating that the network specified is not present. No worries, we'll create a network named mynetwork to resolve this issue. Perfect. Let's do Docker Compose up. Looks like it is running. Let me stop it and rerun in detest mode. Next, let's check the Kafka UI from my local environment to ensure everything is functioning as expected. Let me refresh it. Yeah, it's coming up. The Kafka cluster is up and running, but we don't see any connector yet. Let's create one to establish the connection between Kafka and PostgreSQL. Before creating the connector, we need to ensure that the VM's public IP is whitelisted in the PostgreSQL engine's firewall. Let's go ahead and do that. Copy public IP of VM and go to Postgres. Go to Connections, Networking, give it a name, VM Connect to Postgres. Put IP in CIDR format. Fantastic. Now that we have VM's public IP whitelisted, let's proceed with creating the connector in Postman. Let's create a connector now. Open Postman. Put the public IP of VM in the URL. Let's hit the request. We can check in Kafka UI. Yup, connector is successfully created. Let's head back to see the topics with records. With the connector in place, we'll now open IntelliJ and change the IP of Bootstrap server and check if we are able to load data to S3. Go to controller and run it. Check AWS S3 to see if the folder is created. Keep refreshing and we should see the data appearing as well. Yeah, congratulations, our data is flowing seamlessly from Kafka to AWS S3. Finally, we have arrived at the last crucial step. The main difference between our current setup and the one for production lies in the Dockerization of your Spark-Scala code. So let's do it. First, head over to ecart-migration folder where we have the Docker compose. By running this configuration, we'll have one master node and two worker nodes up and running. Fantastic. We now have our multi-node Spark container ready to go. Now let's rebuild the artifact, ensuring that the correct Bootstrap server is in place for production. Wait for artifact rebuilding. Now that the artifact is rebuilt, it's time to go inside the container that has the master node. Create folder myjars. Now come out of the container. Use the docker cp command to copy the artifact inside the container. With the jar now inside the container, let's run it and head to AWS S3 to check if data is successfully loaded. Yeah, so our data is now seamlessly flowing into AWS S3. If you plan to use this video as a reference for production deployment, there are few essential considerations to keep in mind. First and foremost, ensure that the S3 configurations are not present in the code. Instead, store them securely inside the secret manager. This approach adds an extra layer of security and prevents sensitive data exposure. Moreover, it is advisable to host the jars in a Nexus artifactory. Centralizing your artifacts in a reliable repository facilitates better version control and simplifies management across different environments. To optimize resource utilization, consider mounting volumes for both the Kafka cluster and Spark multi-node containers. This allows for efficient data sharing between the containers and minimizes disk space usage. Lastly, for better code readability, use proper variable names instead of generic placeholders like temp test. Meaningful variable names significantly enhance the clarity and understanding of your code base. If you enjoyed this video and found it beneficial, please do subscribe to the channel. It helps to grow the community and reach more data enthusiasts like yourself. Thank you.